We have developed a method, not a theory, and I must stress that, to predict the mass energy and radii of all fundamental particles. Now this acts to quasi-unify particle physics, and theoretical formulations in particle physics may be tested against our method for validity. What we've developed is a tool, and it should be looked in that light. The method that I'm talking about is based on imagining that all mass radiates a spectrum of photons, and none of what you will see here today contradicts the standard model in any way. Okay, what are we going to cover? I realise we're short on time, so we're actually going to cover quite a bit. I might just skip through this, and you'll see in the progress of time actually what we're going to do. But it's all centric around mass and size of fundamental particles and harmonic descriptions thereof. What is a photon historically? Well, that's been done to death over the last couple of days, so I'll pass that too. Does it have mass? Well, depending on who you talk to, it does. The particle data group estimates its mass energy threshold to be that value. We calculate, now that's based on observational evidence and interpretation of the data. We calculate that threshold value to be within 4.3% of their value, but we do it precisely using Fourier harmonics. As a consequence of that, we go on to calculate its precise mass energy to be 3.25 by 10 to the minus 45 electron volts. And subsequently, a graviton we calculate to be precisely twice that value, 6.4. Does it have size? Well, you know, that's a bit of an open question, but as an engineer, to me, zero anything, I can't work with it. So I have to assume that it does in fact have size to begin with. When we work the problem and work the numbers, we calculate that its diameter to be precisely the Planck length. And as you know, or I'm sure you're aware, this is in agreement with quantum physics models. How did we calculate it from first principles? Well, it was a 5-step method basically. We used initially dimensional analysis techniques, Buckingham pi theory. This method here is 150 to 200 years old. It is responsible for the vast majority of thermodynamics and fluid mechanics knowledge that we currently have. It's an experimentally based method. We then apply the equivalence principle to the pi groupings that are generated from this first step. Subsequently, we apply Fourier harmonics to the second step, to the equivalence principle. The fourth step, we apply zero-point field theory to the Fourier harmonics, and then finally we apply the polarizable vacuum model of gravity to the zero-point field. Now, the polarizable vacuum model of gravity is completely isomorphic to GR. It was in the weak field, but recently, or some recent work means it's the same right across the board now. Okay, what else can we learn from its mass and size? This is extremely important. In our formulation of the mass energy threshold, we use Euler's constant. Now, Euler stated in 1735 that it was worthy of serious consideration. This constant is a purely mathematical construct. It has no current physical meaning. It's extremely important in mathematics. It cuts across many areas, including the Riemann zeta function, and physical verification of what we're actually saying here, of the mass energy of a photon, suggests that gamma has a natural physical limit. Now, to cut a very long story short, that is effectively, putting it simplistically, the same as saying infinity actually has a finite value. It's very large, but it does have a finite value. That's effectively, not the same, but simplistically what we're saying. What other particles can we determine the mass and size of based on a photon method? Everything. Everything that is in the PDG, particle data group database. Okay, what particle predictions have been experimentally verified to high precision? Basically anything that has been measured to high precision agrees completely with our photon method. This includes the root mean squared charge radius of a proton, to amazing accuracy, the classical RMS charge radius of a proton, the electric and magnetic radii of the proton, and the magnetic radius of the neutrons reported by Hammer and Meissner. It all falls straight out. We also get the neutron mean squared charge radius as reported by Kamenov. In fact, just to give you an example of that, the measured value, which is a negative squared quantity, in fact by our rationale is actually quite a gross determination. We can be a lot more accurate than what can be physically measured. The top quark mass energy, again, we get very precise values for that in agreement with observation of top events by the D0 collaboration, and I'll cover that a little bit later on. Okay, here what we actually call our photon method is EGM, electrogravimagnetics. I'll just draw your attention to this column here and just focus on the errors. Here we have our prediction, experimental prediction, with the exception of the classical radius there. The largest error that we get is less than 0.82%. Now, if you also include experimental uncertainty, in fact, the answers that we get are exact. Okay, now, what particle predictions are experimentally implied by a method? Well, basically everything else. That includes the RMS charge radii of all quarks as generalised by the Zeus collaboration, the mean square charge radii of all neutrinos based on experimental observations by the Sudbury Neutrino Observatory, and the RMS charge radius of an electron from scattering experiments as reported by Milani. Now, for those of you who don't know, I mentioned Zeus collaboration, D0 collaboration, CELEX. These are very large international efforts with access to billion-dollar facilities, etc. It may surprise you that we do not have access to that. Okay, what is the mathematical pattern responsible? That's basically it there. It's extremely simple. It is effectively the ratio of two spectra. As I mentioned opening up, we consider or we imagine that all mass radiates a spectrum of photons. Whether it actually does or not is irrelevant. This is a method, not a theory. It's beside the point. When you think of it like that, you've got a starting frequency and a terminating frequency. Here, the terminating frequency, or the harmonic cutoff, is what we call it. And that spectrum can be generated just using Fourier harmonics. The ratio of the cutoff frequencies from a reference particle to whatever you want to know is formulated by that equation there. So if I move on to the next slide, this is quite important. It talks about the harmonic patterns that form. Here in black text we have existing particles. The red text is theoretical particles that we're actually predicting exist beyond the standard model. If I bring your attention down to this section here, if we use the up quark as our base reference particle, and we want to describe everything else in relation to that, we can harmonically. The sequence here is quite obvious: 1, 2, 3, 4, nothing, nothing, 7, 8, 9, 10. It doesn't take Sir Isaac Newton to figure out that 5 and 6, are missing numbers. Here, I'll just cover this very briefly. Here, I just wanted to show you that here's our prediction for the mass energy. Here's what the particle data group says. Here we also include specifically the precise missing particles, the mass energy, there. Okay, what else does our photon method predict? These three simple equations relating the fine structure constant and pi. Okay, this is exact. You plug the numbers in, bang, out they come. We also get the Casimir force to within 0.01%. This is using all the same equations, by the way, all the same method. Okay, and we also predict that the Casimir force is different on different planets. The classical representation does not. It's the same everywhere in the universe. What else do we predict? We're also able to make an experimentally implicit calculation of the Planck length based on experimentally verified proton and neutron radii calculations. This results in a rescaling of the Planck length by about 16%, or precisely cube root of pi on 2. We also predict a gravity experiment, but that's for another day. What we've done is quasi-unifying particle physics, derive the Casimir force, and we've also provided an experimentally implicit definition of the Planck scale. So what does all this mean? Photons, we can explain everything in terms of photons. The gravitational spectrum is a simple but extreme extension of the EM spectrum. There may be 5+ particles that can still yet to be discovered, short-lived, and photonics is important, and that's it. And I hope I made it through with the time.